The quantum crossroads, one world or infinite branches. At this crossroads in quantum theory, the many worlds interpretation offers a radically simple answer. The universal wave function is not just a calculation tool, it is physically real, and branching is an unavoidable consequence of its smooth, unitary evolution without collapse. In this account, quantum mechanics never chooses a single outcome. Instead, every possible result allowed by the wave exists, each in its own branch, and all branches together make up reality. When most people hear many worlds, though they tend to imagine the tropes of science fiction, parallel Earths with wildly different histories, or neat timelines that can be crossed if you find the right machine, that picture misleads. In modern physics, many worlds describes an unbroken, continuous process occurring at the smallest scales. Every time a quantum event unfolds, any situation where the probability wave allows more than one result, the structure of reality incorporates all those results. There's no dramatic fracture, just steady, microscopic accumulation of differences as branches form. Quantum event can be as unremarkable as an electron taking one path instead of another in a microchip, or an atom releasing a photon now rather than a nanosecond later. Before any measurement, such alternatives coexist in the wave function. Afterward, in the many worlds view, each is real in its own branch. These branches are not separate universes floating side by side in space. They are distinct components of the single universal wave function, which evolves without discarding any terms. The branching is constant, happening in countless systems around you at every moment. In everyday terms, branching unfolds quietly, even when you seem perfectly still. The molecules in your body are constantly involved in quantum processes with multiple possible outcomes. Every one of these outcomes plays out in some branch. The sheer pace and number of these events make the branching structure unimaginably vast. Attempting to list even the splits of the last second would be hopeless. From your own perspective, though, you never sense this multiplication. You experience a single, continuous history, the sequence of events corresponding to just one path through the branching web. Suppose a quantum coin could land on heads or tails with equal probability. In this interpretation, both happen one in each branch. In the heads branch, a version of you saw heads. In the tails branch, a version saw tails. After the split, their futures diverge independently. Why don't these versions interact or exchange information? This is where decoherence enters. Decoherence is the process by which different outcomes, though part of the same overall wave function, rapidly lose the ability to interfere with each other because of their entanglement with countless environmental degrees of freedom. Once that entanglement happens, the branches are effectively sealed off. Each continues to evolve according to the same laws, but the correlations that tied them together fade beyond retrieval. Decoherence explains why the branching appears clean and why you feel locked into one branch. However, as research points out, it doesn't by itself solve the deeper measure and probability questions. Physicists like David Deutsch and David Wallace have developed decision-theoretic approaches to explain how the standard quantum probabilities might emerge within many worlds. Others, like Lev Vaidman, have critiqued these ideas or offered alternatives. The mechanisms are under active debate, even among proponents. Understanding this split between mechanism and interpretation is easier if we separate the ideas. Branching means that all possible outcomes of a quantum process remain in the universal wave function. Decoherence explains why those outcomes stop interfering and act like separate worlds. Your perception of a single, unbranching reality is simply the subjective view from inside one decohered branch. This interpretation also reframes familiar cause and effect. Each moment in your life sits on the surface of a vast tree of branching possibilities. Walk through a doorway and photons scatter into your eyes in one particular way in your branch, but in another, slightly different scattering pattern in another branch. The differences are often microscopic and unnoticed, but they stack over time. Eventually, they add up to visibly different events. Conversations taking new turns, decisions coming out differently, hazards avoided or encountered. If you want a mental model, picture a river that endlessly channels into smaller streams which themselves divide again and again. In many worlds, there is no pause in the splitting and no smallest possible branch to stop at. Your current sequence of moments is one channel of that river. Nearby are other channels that shared your past up to some tiny event but now flow elsewhere. Applied to human survival, the logic has a peculiar consequence. If some event has two possible results, survival or death, then in this framework both happen. Some branches end the line of moments that contains you, but in others, the surviving version continues. Across a series of such events, there will always exist at least one chain of branches in which you survive each time. Inside that chain, the experience is one of uninterrupted continuity. Outside it, the overwhelming majority of branches end differently. Importantly, many worlds doesn't single you out. Branching is not about observers, it applies to every physical system. You, your body, and your consciousness follow the same rules as any other collection of particles. The version of you in one branch will never recombine with the version in another. Even if they remain nearly identical in the moments after split, different quantum events will quickly nudge them onto paths that diverge further and further. Rather than a tidy set of parallel universes with defined edges, the picture is one of a single, ever-expanding, intricately connected wave function. Every branch contains its own self-consistent history, all running forward under identical physics. The you in each branch exists only within that branch's chain of moments, while other branches carry different sequences you will never encounter. None of these branches is privileged, all are part of the overall physical state. Grasping this model gives context for why the quantum immortality idea exists at all and why it is controversial. It emerges not from fantasies of world hopping, but from the internal logic of applying many worlds to situations with life and death stakes. And while decoherence makes the branches behave like separate worlds, deep questions remain about how to weigh or interpret them when it comes to probabilities or subjective experience. The next step is to bring this down from the grand, cosmic scale to something more concrete. Instead of imagining improbable survival as an abstract path through a theoretical branching structure, consider how the same logic might play out in a setup you could literally power on with equipment that already exists. Once the scale changes, the mechanics stay the same, but the experience becomes far more personal. Immortality by statistical elimination. Consider a purely hypothetical setup designed only as a thought experiment. On your desk is a small, sealed quantum circuit connected to a device with two possible outcomes, a green light for safe and a red light for danger. Each outcome would represent the difference between continuing as before or meeting a severe, irreversible endpoint without any actual harm taking place in reality. This is purely imaginary, a stand-in for understanding the idea without crossing ethical boundaries. Physicists and ethicists alike warn that such experiments are hypothetical and morally impermissible. They are tools for thought, not action. In fact, leading researchers such as Anthony Aguirre have explicitly stressed that quantum suicide scenarios must never be attempted in practice. In this imagined setup, the device is programmed so that the color it shows each time is determined directly by a quantum event, something inherently unpredictable even with complete knowledge of the system. No concealed algorithm or hidden mechanical randomness is involved. The result comes from the indeterminacy built into quantum physics itself. When you play, you activate the circuit, it enters a delicate state, and a fraction of a second later reality picks one path, green light or red. In our safe mental model, a red light would simply signify you're out in the rules of the thought experiment without any actual injury. Under the standard single-world picture, every press of the start button has a set probability of yielding green and a complementary probability of yielding red. If you play enough times, those odds multiply out to make uninterrupted survival through many rounds astronomically unlikely. In a familiar probabilistic sense, small losses accumulate until one ends the sequence. In the many worlds description, things unfold differently. The quantum event doesn't eliminate one possible result, it realizes both. In one branch of reality, the device shows red, and by the rules of the thought experiment, your participation ends there. In another branch, it shows green and you continue to the next round. These branches are completely separate, nothing from the red path bleeds into the green and vice versa. But in your own experience, you inhabit only the branch in which you see green. The timelines where you didn't are inaccessible. Repeat this enough times and the branching becomes immense. On the grand scale, most branches terminate quickly, consistent with the single-world expectation. Yet there will always be at least one branch where the green outcome appears every time. In that branch, you pass every round, no matter how improbable. It exists because quantum mechanics permits it, and in many worlds, anything permitted happens somewhere in the wave function. From inside that uninterrupted survival path, you feel nothing unusual. There's no signal that you are in the rarest possible sequence of events. The improbabilities don't accumulate in a way you can sense, they simply never happen to you. What would feel like extraordinary luck from the outside reads as ordinary continuity from within. You've never personally experienced the red outcome, so your memory contains only a streak of greens as if that were the norm. This framing is what gives quantum immortality its provocative appeal. If many worlds is a correct account of physical reality, there is always a branch in which you make it through the next event alive. The exact probability doesn't matter as long as it is non-zero. Following only the safe branches, in principle, you never encounter your own death. Mathematically, it means your path always lands on the surviving side of the outcome split, however absurdly unlikely that seems in the larger picture. Replace the harmless lab device with the unplanned hazards of ordinary life, and the logic holds. The world is full of small uncertainties, slight shifts in timing, molecular interactions, environmental fluctuations where outcomes differ microscopically each time. Most of these changes are inconsequential, some aren't. Occasionally, the spread of possible results includes one that stops your story entirely. In the branching view, there is always some fraction of branches where that doesn't happen. The result in such a model is not a life free from danger or harm, but one in which fatal outcomes never land in your own sequence. You can still be injured, still suffer, still take risks and lose, but never in a way that fully ends your conscious perspective. A run of close calls, recoveries against the odds, or unlikely escapes might pepper your life, but to you that would feel like the natural way events have always unfolded. After all, you would have no memory of the branches where they didn't. From the outside, in the space of the universal wave function, this continuation is unspectacular. Your endless chain of safe results is just one of countless patterns, and most others do not resemble it at all. Nothing in the physics gives that chain preference. It draws significance only from being the path you occupy. From the interior view, the rest of the structure is inaccessible, so the singularity of your streak is invisible. It's here that the thought experiment shifts in tone. The survival branch might block endpoints, but it includes every other kind of outcome. That means it can contain prolonged illness, accidents that maim but don't kill, losses with no recovery, anything short of complete cessation. The principle, if real, is stark: continuity without any guarantee of quality. To imagine it as a universal safety net is to misunderstand its scope. It's not protection from harm, only from annihilation. Even stripped to a safe, binary device on a desk, the mechanism in this hypothetical is the same principle behind the more dangerous images people attach to quantum suicide. In a collapse-based view, improbably long streaks happen only rarely and end naturally. In a branching view, such a streak must exist somewhere, and if you are in it, every elimination event filters out the branches where you were. The apparent miracle is just the flip side of ordinary probability. Your experience is restricted to the survivor path because all others, by definition, contain no more of you. This reversal of statistical expectation is the core of immortality by statistical elimination. In normal probability, non-zero risks compound to produce near certainty of eventual loss. In the many worlds framing, even the smallest survival chance produces a path where loss never occurs, and for the observer inside it, that path is the only reality experienced. The unsettling part lies in picturing what it would be like to remain on that path for as long as quantum events unfold, watching other stories end while yours carries on unbroken, with no moment when you can observe how rare your situation really is. Understanding this logical inversion sets up an important context. It invites questions about how you might usefully explore such branching in safe, controlled, and entirely hypothetical ways, and what technologies could model it without crossing any ethical lines. Recent breakthroughs that make this less science fiction. In early 2025, the headlines in quantum research were full of results that even a few years earlier would have seemed out of reach. Laboratories working with trapped ions and photonic links reported high-fidelity teleportation of qubits over distances far beyond a single experimental table, reaching scales that connected entire facilities. In practical terms, researchers could now create entangled particles, separate them by many kilometers, and maintain their shared quantum state long enough to perform operations with accuracy levels that avoided the need for constant redundant checks. Fidelity numbers: how precisely the transmitted quantum state matched the original past thresholds that had only appeared in theory, with error margins so small they could be relied upon without excessive repetition. Entanglement itself has been a known phenomenon for decades, but preserving it over these distances without its delicate correlations collapsing to environmental noise has always been the bottleneck. Improvements here weren't the product of a single breakthrough, but of incremental gains in isolation, shielding, and control, better vacuum systems, more stable cryogenic enclosures, and laser pulse sequences tuned to minimize disturbance. Each refinement shaves away at decoherence, allowing those fragile quantum relationships to persist for far longer than before. At the same time, new fabrication techniques are transforming the qubits themselves. For example, in 2025, NIST SQMS reported major qubit fabrication and coherence improvements, using advanced encapsulation and precision nanofabrication to dramatically extend the lifetime of superconducting qubits. Other arms of the field pushed on very different frontiers. In 2024-2025, TU Dortmund demonstrated a time crystal system persisting for more than 40 minutes, an astronomical leap over previous lifetimes. And a Science Advances paper described Bell inequality type violations using indistinguishable photons, tightening the experimental grip on questions of non-local correlation. These kinds of results expand the range of quantum behavior scientists can test directly, but they don't prove or disprove specific interpretations like many worlds or the idea of subjective immortality. What they do is give researchers a much broader and more precise toolkit for observing, manipulating, and linking quantum events in the real world, so that experiments can be designed to probe the dynamics underlying those interpretations more closely than before. One application of these refinements has been in quantum teleportation experiments, where the state of a particle is destroyed at its origin and reconstructed at a distant site using both classical information and an entangled partner as a carrier. Reliable long-distance teleportation depends entirely on sustaining high-quality entanglement, because any corruption in the correlation between the two particles will degrade the transferred state. Extending teleportation over kilometers without performance collapse allows quantum events in one location to influence linked outcomes in another, still bounded by quantum unpredictability but now separated in space without loss of coherence. While this isn't the cinematic version of beaming objects, it is the dependable transfer of quantum information, an essential component for future distributed quantum systems. In parallel, the performance of quantum computing hardware has been accelerating. Early generation machines suffered from such high error rates and slow gate speeds that deep computations were pointless. The system would decohere long before completing a useful sequence. By 2025, industry and academic platforms alike were reporting both significantly higher gate speeds and sharply reduced error probabilities. Faster gates mean an algorithm can be executed in less time, avoiding some decoherence losses, while lower errors mean fewer corrective cycles, freeing qubits to focus on computation instead of constant state repair. Although the media often focus on headline applications like breaking encryption or modeling complex materials, these hardware advances have another less flashy purpose, making it practical to simulate quantum systems in detail. A chain of entangled measurements is mathematically a multi-branch structure, and simulating it demands resources that grow beyond classical computing very quickly. Stable, fast qubits allow researchers to evolve these branching probability landscapes over time, tracking how different possible outcomes appear, change, or vanish as the quantum system interacts internally and with its environment. Such simulations can't settle whether those branches represent literal parallel worlds, but they can make the connection between theory and behavior far easier to grasp. Instead of an abstract probability table, you can watch a simulated state change shape as events multiply the possible outcomes. Gains in stability mean these virtual branching trees can be extended deeper without drifting into meaningless averages from accumulated errors. For many researchers and students, this shift turns diagrams in a textbook into something closer to a working model you can interrogate step by step. High-fidelity links add a physical dimension to these models. By tying parts of a simulation to real qubits in distant labs, each part measured and fed back into the system, you can create demonstrations that show linked quantum outcomes arising in separate places in real time. This reinforces the point that quantum randomness is not constrained to one location. The constraints are imposed by decoherence and measurement, not by distance. With these tools, researchers can stage controlled, statistically extreme scenarios in a way that was only theoretical before. Linking a sequence of entangled decisions and watching how long a single improbable path survives before reverting to the expected distribution can now be done without pushing the hardware beyond its limits. The data from such runs not only illuminate how correlations degrade over time, but can also test how robust linked outcomes are when stressed by environmental noise or rapid repetition. The fact that such chains can be maintained by current machines marks a shift toward practical exploration of quantum probability structures, even if the setups are many orders of magnitude removed from the life and death frames of thought experiments. The important point is whether these demonstrations reveal evidence for or against any particular interpretation. It's that 2025-era technology can now sustain and manipulate quantum states with enough control to make those interpretations more than abstract debates. Models can run longer, experiments can link more components over greater distances, and measurements can be taken with fewer compromises. In effect, experimental reach is catching up to the kinds of scenarios that, until recently, could only be described verbally. For the wider audience, the takeaway is subtle but significant. Elements that once seemed like set dressing for speculation now appear as live, measurable phenomena. Entanglement over long distances, precise gate operations, extended coherence times, and simulations that map the full range of possible outcomes over many connected events are not hypotheticals. They operate in labs today. The improbable outcomes central to certain interpretations sit alongside the likely ones within these models, and both can be assigned measurable probabilities that shift predictably as the systems evolve. None of this confirms that someone could, in any personal sense, follow an endless thread of survival through branching events. What it does is strip away some of the former distance between abstract theory and what can be physically arranged, observed, and calculated. Linked randomness, persistent correlations, and branching style structures can be seen in action, under conditions choreographed by the experimenters. It changes the conversation from "this is what the math suggests could happen" to "this is a functioning quantum system whose measured parameters match the same equations." By closing that gap, the new tools also raise another issue, one that no improvement in coherence time or gate speed can settle. After all, showing that a quantum system will produce every allowed outcome still leaves open a human-specific question. When the branching happens, what fixes which outcome you personally experience? Consciousness, the missing variable. In the middle of the wider conversation about branching universes, another question keeps pressing for attention. Could consciousness itself be part of the machinery? Quantum mechanics, as it is normally written, says nothing about minds. The equations describe systems, measurements, and outcomes in entirely physical terms, and in those terms branching happens whether anyone is there to witness it or not. Still, to anyone actually having an experience, reality always comes as the one you are aware of. Whether that connection is only coincidental or points to a deeper link remains unsettled. The straightforward position treats the mind as a classical system. Neurons fire, chemicals diffuse, and electrical impulses travel along axons. Thoughts, memories, and decisions emerge from networks of physical interactions that, however complex, behave like other large-scale processes. In this view, your brain is no more relevant to quantum physics than your pancreas or your skin. Consciousness is an emergent effect of parts interacting, not the product of delicate quantum states, and the branching of events after a quantum process has nothing to do with what your brain happens to be doing. Some researchers, however, have argued there may be room to question that separation. Since the 1990s, and with more activity again in 2024-2025, cross-disciplinary teams have begun probing whether certain brain processes might involve quantum effects in ways classical models miss. Notably, recent experimental work by Joseph Wiest at Wellesley reported that microtubule binding drugs can alter anesthetic response in rodents, a finding that intersects with older theories linking microtubule dynamics to cognition. Exploratory collaborations, such as projects at the Allen Institute, are also mapping neural and molecular structures with an eye toward whether quantum-sensitive interactions could have functional roles. These projects are still far from presenting proof, but they have prompted renewed, careful discussion about whether trace quantum behavior in the brain is possible. Mainstream neuroscience remains cautious. Figures like Christoph Koch at the Allen Institute and physicists such as Max Tegmark have pointed out that the brain's warm, wet, noisy environment is exactly the kind of setting where quantum coherence should evaporate almost instantly, drowned in thermal noise. Tegmark's calculations suggest any coherent quantum state in neural tissue would decohere in times far shorter than a neuron's signaling window, making it unlikely to directly influence thought. The prevailing consensus is that ideas about quantum processes as the source of consciousness are speculative and not supported by the bulk of available evidence, even if small-scale effects aren't yet completely ruled out. Some of the renewed interest comes from scale and timing. Neuronal substructures, microtubules, ion channels, vesicle release sites operate in regimes not wholly removed from where quantum effects can set statistical biases. If in principle some quantum-level change could nudge the timing of a neuron's firing, and if patterns of such firings underlie conscious moments, then the mental narrative and the unfolding of physical events might be less independent than assumed. So far, though, this remains an if-laden scenario without direct measurement to support it. That's why early claims linking consciousness to branching have been treated warily. To actively influence which branch continues as your experience, a mental state would need to participate in something like the collapse or effective collapse of a probability wave. That task demands a precise definition of measurement and a coherent physical account of awareness, neither of which is within reach. Without predictions that cleanly separate a consciousness selects branches process from ordinary decoherence, these remain intriguing thought experiments rather than viable laboratory tests. Still, there's an everyday pull to the idea. Subjective awareness feels like a single, continuous thread, not a blur of equally real alternatives running in parallel. When you wake, you pick up where the day before left off. You don't perceive yourself as spanning many almost identical mornings. That stubborn continuity gives the impression of selection, whether or not the physics grants you any steering role. One way to frame it is through a vignette. Imagine your awareness as a stubborn app on a phone, something that simply refuses to close. Try to swipe it away, shut down the phone, or drain the battery, and when the system restarts, the app is still there in the foreground. In a branching context, each offloaded tab or clone process would be like a version of you in a different branch, running somewhere unseen. But the one in front of you now is the only one you directly inhabit. If the app never closes in this branch, continuity persists. In the strong version of the theory, this persistence is what quantum immortality relies on. Wherever the branching produces multiple possibilities, you only ever occupy those in which your awareness is still active. Outcomes without you are, by definition, inaccessible. They fade from your personal record not because you left them, but because there is no you there to observe their unfolding. In versions that give consciousness an active role, your presence wouldn't just be surviving. Your being here would help define which branch counts as survival in the first place. The stakes, if that were right, would be enormous. It would suggest that the reason you remain alive through improbable strings of events could be a property of awareness itself. But even the scientists most closely involved in quantum theory emphasize the gap between such speculation and evidence. The current experimental probes, whether measuring microtubule responses in animals or mapping neural dynamics with quantum-tuned sensors, are exploratory, not proof. For now, the more defensible statement is that nothing in standard quantum mechanics requires consciousness to influence branching, and nothing in mainstream neuroscience shows that it does. The possibility remains open enough to keep interdisciplinary discussions alive, but the balance of opinion holds that cognitive processes are classical unless shown otherwise. Explorations by groups such as those at Wellesley and the Allen Institute may uncover interesting biology, but whether any such findings would rewrite our understanding of consciousness is anyone's guess. That lingering uncertainty is part of why the question keeps resurfacing, because if any link between awareness and branching were confirmed, it would ask us to rethink both the physics of the micro world and our place in it.